In this video, we're going to be talking about lines and planes in space. So in the plane, which would be like the XY plane, for example, it's got two dimensions. We use slope to determine the equation of a line. But in space, where we might have three dimensions, X, Y, and Z, we're going to use vectors to determine the equation of a line. So remember, in the plane, you had y minus y1 equals m times x minus x1. And m was the slope, and x1, y1 was the was a point that the line went through. So we're going to see how that translates to 3 space, so x, y, z. So remember vector notation, v, and you might see an arrow over this v if you're using your handwriting, is some triple coordinates ABC. And this is a line through the point P, x1, y1, z1, so you can see that here. And then the vector is the standard position of that line, so in the same direction as that line. So the vector v we call a direction vector for the line L, and A, B, and C are the direction numbers. And just kind of as a side note, it's important to remember you may see this written in either of the formats with the coordinate component form like this, or you may see a vector written in vector form where you'd have, or unit vector form, AI plus BJ plus CK. So those mean the same thing. So let's talk about how we represent a line, or we describe a line. So one way that you can describe any curve on a graph is a set of points. So we could say that the line L consists of all points Q, X, Y, Z, for which PQ is parallel to V. Or in other words, PQ, that vector PQ, is some scalar multiple of V. So PQ would be x minus x1, y minus y1, z minus z1, or at, bt, ct, so this is just all of the components of v multiplied by t, or you might see that written as the t times the vector v. So there's several different ways that we can represent that line. So coming from this, if you want to think of each of these components being equal to each other, because that's the convention of a vector, is if it's in the same position, it's equal, if two vectors are equal. This would mean that x minus x of 1 is equal to at, or you could write x as x of 1 plus at. And of course you can do this down the line with y and z as well. And if you do that, you get what's called the parametric equations of a line in space. So a line L parallel to the vector v equals abc, passing through the point p x1, y1, z1, is represented by the parametric equations x equals x sub 1 plus at, y equals y sub 1 plus bt, and z equals z sub 1 plus ct. And of course, the x1, y1, z1 come from the point P, and the a, b, and c come from the direction vector v. Now, assuming that all the direction numbers are non-zero, if you eliminate a parameter, the parameter t, and solve for t, you can then set those three versions of t equal to each other and get what's called the symmetric equations for a line. And this is going to be more familiar with what we're used to with the point slope form in 2 space. It just doesn't have the z basically attached to it. So again, this only works if a, b, and c are not equal to 0, all not equal to 0, because if one of them was, then you would have an undefined term there. So this is a pretty simple example. It says find sets of parametric equations and symmetric equations of the line through the point -2, 0, -3, and parallel to v equals 2i plus 4j minus 2k. So we're given two things here. We're given our direction vector, which is v equals 2, 4, -2. That's the a, the b, and the c. And we're given our point P, which is -2, 0, -3. So this is our x1, y1, z1. So our parametric equations in terms of t, where t is the parameter, are x equals -2 plus 2t. That's the x of 1 plus at. Y equals 0 plus 4t. And z equals negative 3 minus 2t. The only part that's difficult about this at all is just making sure you get a, b, and c in the right place and x1, y1, z1 in the right place, because that doesn't matter. Okay, so for symmetric equations, if you don't remember the formula for it that's above, you can solve for it pretty easily. You can take these different equations, and we've got x equals negative 2 plus 2t, so I would add 2. And then I would divide by 2 to get x plus 2 over 2 equals t. For y equals 4t, I would divide by 4. And for z equals negative 3 minus 2t, I would add 3 and divide by 2. Now, since we have 3 different things that are all equal to the same t, then that gives us x plus 2 over 2 equals y over 4 equals z plus 3 over 2. So that would be my symmetric equations, and this would be my parametric equations. One thing that is important to note is that if you use a different point on the line, you will get a different looking set of parametric and symmetric equations, but they will represent the same line, so it would still be a correct representation of that line. Okay, so this one says find set of parametric equations and symmetric equations of the line through the point 1, 0, 1 and parallel to x equals 3 plus 3t, y equals 5 minus 2t, and z equals negative 7 plus t. So it's important to recognize here that this is very similar to those problems you've been doing since junior high or high school, whichever course you encountered it in, where you had to find the equation of a line with through a given point and parallel to a given line. So they've just given you the parametric equations of the parallel line here. So this is, remember, x of 1 plus at, so a equals 3 from this 3, b equals negative 2, and c equals the 1 that's understood to be here. So your direction vector v is 3, negative 2, 1, and your point is 1, 0, 1. So our parametric equations would be, for our line, x equals 1 plus 3t, y equals 0 minus 2t, and z equals 1 plus t. And then using the symmetric, or to find the symmetric equations, you can either solve these for t, or if you use the formula, you would have x minus x of 1 over a equals y minus y sub 1 over b equals z minus z sub 1 over c. And we typically leave it like that. We don't usually, in this format, multiply through by a number. Now here's another example. It says find sets of parametric equations and symmetric equations of the line through the points 7, negative 2, 6, and negative 3, 0, 6. So for this one, this is just like the kind of idea where you had to find the equation of a line between two given points, and you had to find your own slope. But remember, instead of slope, we're going to use vectors. So our direction vector is going to be the standard position of PQ if this is P and this is Q. And it doesn't really matter which order you put it in. That's up to you. I'm just going to go from P to Q. So I'll have negative 3 minus 7, 0 minus negative 2, and 6 minus 6, which will give me negative 10, 2, and 0. So this is my A, B, and C. So my parametric equations, and remember with this you can use either point you want to. It's just going to look a little different, but it will represent the same line. I'll use P, so this will be my x1, y1, z1. So we'll have 7 minus 10t. We'll have y is negative 2 plus 2t. And we'll have z is just 6 plus 0t. So that will be my parametric equations. Now my symmetric equations, we would have x minus 7 over a, which is negative 10, equals y minus a negative 2 over 2. And I mean, we can't technically do the z minus 6 over 0 because of that 0. So whenever there's a 0 in the denominator, this means that for this parametric representation, it doesn't matter what t is, z is always 6. So if you wanted to describe the line, you would say, well, it's all the points such that this is true and z is equal to 6. So basically what this is it's a line that is in the xy, or in the plane that is parallel to the xy plane but happens at z equals 6. So it's just basically raised above the xy plane. And I was telling you guys earlier, you know, when you start with this format, if you wanted to see what that looked like in point slope form, since we don't have a z as part of the symmetric equation, you can multiply through by, say, a 10 to clear out these fractions, and you can see the point slope form with m equals negative 1/5. So there is a relationship here with the symmetric equations especially to our point slope form in 2 space. We've just added that extra dimension.